Welcome back today to today's tuition. Um, this question says that solve the equations x plus y equal 9 and x squared minus 3xy plus 2y squared equals 0. The first one is an equation of a line, and the second one is an equation that we call it homogeneous equation of second order. Why? It is a homogeneous equation of second order because you see x raised to the power 2 there, you see y raised to the power 2 there, and you also see that x, being a variable, is multiplied to another variable y. So principally, they are also to the power to the power 2. That's the reason why it is called an equation of a homogeneous equation of second order. If you see any homogeneous equation of second order like this one, which I will explain it into much detail later on, if you see any equation like this, you can immediately recognize it to be called a pair of lines. But in the meantime, my interest is to bank down the solution of this simultaneous equation. Once we are done with the solution of this simultaneous equation, then preferably I'm going to go into much details of the nature of this equation. And this work is going to be very neat work and very extensive work, because there is no point in rushing. For the concern the simultaneous equation, we have it just in a touch. It's not a big deal. But to make the work so beautiful, so more explanatory, into detail, because this is a private tuition, and you deserve the best, and the best has to be given to you. So, but as I've said, we will do an extensive work on this analysis. But the most important thing, the question says that solve the simultaneous equation. We want to know where the points of intersection are. That's the only thing we want to know, and then we will take the analysis further in further explanation, further extension of the work based on this. So in the meantime, let us bank the solution of it. Picking up the first equation is much simpler, so we can have x equal 9 minus y. Then I'll call this one equation 3 at this time. Putting equation 2, putting equation 3 rather back into equation 2 will give us x squared, as you see there, but we see x is 9 minus y, so 9 minus y squared minus 3 y x, where x is 9 minus y, plus 2y squared equals 0. So we have here 81 minus 18y, we're expanding this one, plus y squared minus 27y plus 3y squared plus 2y squared equal 0. Collecting the like terms together, we will have 5y squared, which is this one and this one. And then now we have 6y squared, this one and this one plus this one. We have 6y squared. And then minus 18y plus minus 18y plus minus 18y plus 27y. We have minus 18y. Let's see. Minus 18y plus minus 27y. We have minus 45y. Good. And then we have plus 81 equals 0. Is there further space down there? Then I think we can factorize 3 outside this equation. So we can have 2y squared minus 15y plus 21 equals 0. Is there space there? Yeah. And then we divide both sides by 3. If we divide both sides by 3, then we'll have, dividing both sides by 3, then we'll be left up with 2y squared minus 15y plus 21 equals 0. Then this is a quadratic equation in y. And we can factorize the quadratic equation in y. Oh, sorry, this is plus 27 rather, because we factorize 3 out. This is supposed to be 27. So this is a quadratic equation in y. So we multiply the coefficient of y squared to the coefficient, we multiply the coefficient of y squared to the constant. We will have 54. 2 times 27 is equals to 54. But remember, 54, but also 54 is no different from minus 9 multiplied to minus 6. If we add minus 9 to minus 6, we have adding, we have minus 15. We have minus 15, which is exactly the coefficient of y, which indicates that the minus 9 and the minus 6 are in fact the factors of the factors that are useful for the quadratic equation. In that case, this equation becomes 2y squared minus 6y minus 9y plus 27 equals 0. Then we can do some factorization further. We are picking this one and this one to factorize 2y outside. So from this one and this one, we'll have 2y minus 3. Then the same y minus 3, we'll write it here. And then minus 9 is the appropriate factor that we can put in front of here, because if we multiply the minus 9 to y, we'll have that one. And we'll multiply the minus 9 to minus 3, we'll have 27. So we have 2y. We are factorizing the common factor out. Minus 9y minus 3. In fact, this is the quadratic equation, the solution of the quadratic equation that we did in the previous chapter. We did it. We did an extensive work on that. So if you find it a little bit comic, I mean, you can refer to those tutorial tutorial videos. Now, we can now say that that expression 2y squared minus 15y plus 27 is very much identical to 2y minus 9 y minus 3 equals 0. Good. In this case, we can say that from this equation, I'll call it equation micro. We can say that 2y minus 9 equals 0 and y minus 3 equals 0. When 2y minus 9 equals 0, then y is equals to 9 over 2. And when y equal minus 3, then y equal 3. These results are the y values of intercept when both this one and this one intersect. These are the y values. So how can we find the x values? Let's see whether we have a place here. The x values, we can go to the equation 3 straight away and say that when y equals to 9 over 2, when y equal 9 over 2, then from equation 3, which is x might equal 9 minus y. We have x equal 9 minus 9 over 2, which implies is s equal 18 minus 9 over 2. I cross multiply. So we have x equal 9 over 2. Okay, also, when y equals 3, from here, then using the equation 3, we have x equal 9 minus 3, x equal 6. This one and this one. When y equals to 3, x equals to 6. And 9 over 2, which is when y equals 9 over 2, x equals 9 over 2. So the coordinate of the point of intersection is when s equals to 9 over 2, y is equals to 9 over 2. When s equals to 6, y equals to 3. These are the two coordinates, the 2 points where this equation I call this one lines. I will show you later on that they are lines. They are not. I will show you later on that this is a line called. It's a pair of line. But it is not a curve. Never. It can never be a curve. I'll show it later on to you. So the most important thing at this time is that the solution of this simultaneous equation is when x equals to 9 over 2, y equals to 9 over 2. When x equals to 6, y equals to 3. Now, because the board is fully used, I would like you to take your time to copy everything. I'm going to stand at the other side for you to have a clear board, and you can pause the video and copy everything, and then we'll pick it up from this point. Thank you. So these are the coordinates of the point of intersection where they do intersect. What is this? Honestly, I will show, I know it, but I'll show you how it looks like. It looks like this should be the graph. And you know that the first equation is y equal minus x plus 9. Good. Minus x plus 9. Let me see whether the question is correct. Yeah, it's correct. Y equals to, which is a negative gradient, y x. From here, you see that intersect on the x-axis y is equals to 0, which indicates when y is going to be 0 in this equation, then x is equals to 9, which implies this intersection occurs at where x equals to 9. In some cases, we write it like this way. 9, we write it this way. 9, oh. Now, secondly, intersect on the y-axis, x equal to 0 in this equation. In that case, when x is going to be 0, then y will be equal to 9, which you can also write it like this way. But if you watch this equation carefully, you can see that it is of the form mx plus c, where y-axis intercept is 9, and the gradient is minus 1, a negative gradient. Assuming here is 9 being the y-axis intercept, and here being the 9 being the x-axis intercept, then you can see that line will be something like this. Yeah. And this one, as I've told you, that it is it is a line, it's a pair of lines, and that lines will look like this way. I will later on demonstrate it to you. It will look like this way. It goes this way, and it goes this way as well. passing through the origin. This one is L2, line 2, and this one is line 1. So you can see that the point of intersection that we are talking about is these ones, where this one is L2 and this one is L1. Now, we had the point of intersection to be S equal to, when S equals to 6, Y will be equals to 3, which will be here. This will be the B. The B coordinate. 6 and 3. And the A coordinate will be this one, 9 over 2, 9 over 2. This is the B coordinate, the A coordinate. So this is all what the question was about, and this is the origin. So the 2 points of intersection are the solution of the simultaneous equation, where this one, S squared minus 3x1 plus 2y squared equals to 0. It is not a curve, but it is rather pair of line, that is L1 and L2. Now, in the next analysis, as a matter of fact, we are done with the question whatsoever. The question that we were trying, we were assigned to do it, we have already done it. We have, banged everything down. So, any examiner or any teacher where you can stretch yourself to give, such a neat work to, it will be very much impressive to that person. But we can still go further beyond that, and this is what I would like us to do in the next attempt. So at this time, I would like you to pause the video and copy everything as you see on the board, and then we are going to devote our time to explain why this equation is a pair of lines. This is it. So take your time, pause the video, and then I'll wipe off everything, and then we'll come back again. Now, as I already said, we are going to prove that that line, let me write it down, or that equation, the equation, the homogeneous equation, this equation, S squared minus 3 y x plus 2 y squared equals to 0. This equation, you can write it down as I dictate. This equation is a second order homogeneous equation. Okay. Then I would like us to, it is in the form of, that equation is in the form of a s squared plus 2 plus 2 h xy plus b y squared equal to 0. That's the equation. Second order homogeneous equation, or a homogeneous equation of second order. Now, picking up the left-hand side, which is x squared minus 3y x plus 2y squared equal to 0. Good. We are going to use the quadratic approach, factorization, to factorize this homogeneous equation of second order. To do that, the coefficient of x squared will be multiplied to this one, and this time we make this one as a constant. This is it. In that case, it's a quadratic equation in x, where this one is a constant. So the coefficient of x squared is 1. We will multiply it to the constant, which means we have 1 times 2y squared is equals to 2y squared. But we also know that 2y squared is no different from minus 2y multiplied to minus y. If we add this one, adding them, we can have this one. Adding gives us minus 3y, which is this one, which indicates that this is very good factor that we can pick it up. So we make it x squared minus, instead of 3y, we put 2y minus y plus minus 2y minus y, which is this one. But don't forget, x is there multiplying it, plus 2y squared equals 0. Then we have x squared minus 2y x minus y x plus 2y squared equals 0. We are using this one as the prime factor, we are using this one as a point where factorization begins. So we are going to factorize x out of this and this. So we have x minus 2y. Bam. Then the same x minus 2y, we'll write it here, x minus 2y. How can we have this one and this one? To do that, we have to multiply here by minus y. In that case, minus y multiplied to x, we have this one. Minus y multiplied to 2y, we have 2y squared. Then we have x minus y, x minus 2y equals 0. Good. Which indicates that this equation that we see there is the same as this equation. There's enough space. So, therefore, x squared minus 3yx plus 2y squared is very, very much identical to x minus y. X minus 2y equals 0. I'll call this one equation sigma. I'll call this one equation sigma. So the second, the homogeneous equation of second order, we have seen that, in fact, the left-hand side is equals to the right-hand side, which indicates that this line gives rise to two lines. Now, x minus y equals to 0 and x minus 2y equals to 0. From the first one, we have y equals to x. Maybe we call it equation 4. And from this one, we have y equal half x, which is also equation of a line. Both equation of lines. This one is very much identical to mx m I'll call this one m1x and I'll call this one m2x. They are both equation of lines that passes through the origin. Yeah. So you can see that the homogeneous equation of second order gives rise to two linear equations that passes through the origin. So now you can see that what we said earlier, that this equation, as we see, it is equation of pair of lines. We can now see it here. These are the equation. This equation now is this one. Y equals to x, y is equals to half x. Now, take your time, copy it, and then we'll pick it up from here. Take your time. Now, the first equation was y equal m1. Oh, the first one was y equal x, which was no different from m1x. This equation has a line that passes through the origin. This is y-axis, this is x-axis, and this is the origin. And this one is the line 1, whose gradient is m1. And you can see that there's an angle here. I'll call this angle theta 1. Now, the other one was, maybe I'll change this one. The other one was y equal half x, which was very much identical to m2x. Good. And that line will look like this is y-axis and this is x-axis. And that one will be line L2, whose gradient is m2 and has an angle theta 2. And this is the origin. Okay. These two equations, they emanated or came out from this equation. And that was the reason why we said that this equation represents equation of a pair of lines. So these are the pair of lines. What we are going to do is to sketch the same equations on the same axis. Take your time to copy it, and then I will wipe this session and then we will do it. Take your time, copy. Yeah, we are drawing both, we are sketching both equations on the same axis. We have this one. This is y-axis. And this is x-axis. And the first one goes this is L1, whose gradient is m1, whose angle is theta 1. And that equation is this one. And then you have the other one, which is this one. It is like this. It also goes through the origin. Maybe I have to resketch it. Good. So these lines, L1, sorry, this is L2, L1 and L2 represent x squared minus 3yx plus 2y squared. And then these are their respective gradients. So let us move on to see the angle between the two lines. I'll call it this angle, I'll call it alpha. Maybe I'll call it alpha, the angle between the two lines. Let me see whether you can see it on the board. Yeah, you can see it. But it is not wise to use that color. So I'll still maintain this angle. I'll maintain it to be I'll maintain this angle to be alpha. So the angle between the two lines is called alpha. Between the two lines. Is alpha, where alpha is equals to theta 2 minus theta 1, which if we take tan on both sides, we have tan alpha equal tan theta 2 minus theta 1. You can use, let me call this one equation tau. Good. Now, you can use compound angle formula in trigonometry to expand this one. So we have tan alpha is equals to tan theta 2 minus tan theta 1 over 1 plus tan theta 2 times tan theta 1. Good. Take your time, copy it, and I will still continue the same thing at the other side. Take your time, copy it. Yeah. Welcome back again. This is the pair of lines that pass through the origin. This one is the L1, whose gradient is, this one doesn't look like a line. We should do it properly. The gradient is M1 and the line is L1. The line is L1 and the gradient is M1, y-axis, and this is the x-axis, and the And then you have another line. L2, whose gradient is M2. And then the angle from here to here is the theta 2. And the angle from here to here is the theta 1. And the angle between the two lines, call it alpha. And I said that alpha is equals to theta 2 minus theta 1. Taking tan on both sides, we have tan alpha equal tan theta 2 minus theta 1. The right-hand side, you can use elementary trigonometry approach to expand the right-hand side. Because the angles are not the same, theta 1 is not equal to theta 2, which indicates it is a compound angle formula. So the compound angle formula to expand the right-hand side, so it will be tan theta 2 minus tan theta 1 all over 1 plus tan theta 2 multiplies to tan theta 1, tan alpha. Good. I'll call this one equation I'm calling it equation 5. But remember, gradient, tangent is also a gradient, which indicates that tan theta 1 is the same as m1, and tan theta 2 is the same as m2. In that brevity, then equation 5 can also be rewritten as tan alpha equal to tan 2 theta. Tan 2 theta is m2 minus m1 all over 1 plus m2 m1. Therefore, I'll call this one equation 5. Therefore, equation 5 is similar to equation this equation as well. So it indicates that tan alpha is equals to tan, there's no space there. So I would like you to copy everything, and then we'll conclude at this side. Copy everything as you see here, because this one is vital. That's why I left it. For instance, well, it is not at this time vital, but the right-hand side is vital. The right-hand side is, this is it. So copy everything that you see at the right-hand side here, and then I will wipe it off and then conclude at this session. Thank you so much. Good. Therefore, tan alpha equals to tan theta 2 minus tan theta 1 all over 1 plus tan theta 2 multiply to tan theta 1 is very much identical to m2 minus m1 all over 1 plus m2 multiply to m1. This is the angle between two pair of lines here. So if you want to know the angle of the two pair of lines, this equation, previously we found that equation was y equal half x, very much identical to m2x, which implies is m2 is equals to half, and this line get the equation y equal to x, which is very much identical to m1x. You can see that the gradient m is equals to the gradient m1 is equals to 1. So if you want to find the angle, then you can insert these values over there. In that case, the angle alpha, the angle between them, now this term becomes alpha is equals to tan inverse of m2 minus m1 over 1 plus m2 times m1. Which implies is alpha is equals to tan inverse of m2 is half minus 1 over 1 plus half multiply to 1. And you can use your calculator to find the real value of alpha. Then, thank God, we have brought the whole analysis to conclusion on that specific question, as I gave a promise that I would do an extensive work. And one thing that was also very important that we did solve the simultaneous equation and sketch the graph, and we saw that honestly the simultaneous equation, the other line was this one, and the solution was here and there, as you saw it at the other session. Yeah. So at this time, we believe that we have done such an amazing and such a plausible work. To God be all the glory. We thank God because He's the one who has given us the privilege, to have such understanding. To communicate with you, and you being such an attentive participants of the whole thing. I don't take it for granted. And I thank God for your life. And I'm also grateful for the opportunity that I have, to communicate with you. Until then, I will say that may the living God continue to bless you and continue to give you peace and continue to give you knowledge and wisdom. God bless you. God bless you.